Okay, so here we are to the second part of the Math 021 guided notes for sets and expressions. And we're going to start off here with reviewing the examples for set builder notation. So for the first one, we have to put this set, which is written in roster notation, into set builder notation. And remember, with set builder notation, we always start off with our bracket, and then we have our x, our straight line, which stands for such that, and another x, an e as an element of. And then we have to decide what number or what set describes these numbers the best. And here, because we have 6 through 12, I would either say natural or whole numbers would describe it the best. Since there is no 0 and we don't know, we can say we could do natural. Okay, so it's the set of all x such that x is an element of natural numbers. And for this one, because we have an end and a starting point and an ending point, we have to do a compound inequality. So 6 will be our starting point, and 6 is going to be less than or equal to x, which is less than or equal to 12. And then we put our bracket there, and that's it for that one. For the next one, we're going to start off again with our bracket, and we're going to do x such that x is an element of, and here, because we're dealing with negative numbers and they're whole numbers or opposites of whole numbers, then we are going to say our best set will be integers. And then for my inequality, because we have the 3 dots, we want to look for a stopping or a starting point. And this is actually going to be our stopping point because that's the highest it goes. So we're going to put our x first and then our -5. And because we're going down, x is going to be less than or equal to -5. All right, and our last one here, we go from 10, 11 to 12. So we're going to put our bracket, and we're going to have x such that x is an element of, and here again, you could do natural or whole numbers. I think natural is probably the better bet because we don't see that 0. But if you had whole numbers, that's okay. And then x is, and here our starting point is 10. But this time, x is going to be greater than or equal to 10. And that's it for the set builder notation examples. So here we're looking at algebraic expressions. And an algebraic expression is any expression that contains numbers and letters connected by an operator. And when they say an operator, they mean like addition, subtraction, multiplication, or division. So just some examples of an algebraic expression. You could have, most commonly, we're used to seeing something like 3x, a number and a letter next to each other. And the operator that's holding those together is multiplication, remember, because it's 3 times the x right there. We could have just x plus 5. That's an algebraic expression. We could have y plus x plus z. And that's also an algebraic expression. It doesn't have any numbers that we can see, but there's always numbers because with like the y, the x, and the z, there's always like a number attached to it with multiplication. If we don't see it, it's always at 1. I call it the invisible one. What makes these an expression and not an equation is an expression doesn't have an equal sign. An equation does. So here they're expressions because there's no equal sign. So what we're going to do is first we have a variable, which are our letters. And then a term is a number or a product of a number and a variable. So this right here is going to be a term because product means the answer to a multiplication problem. So 3x is a term. We could also do just x by itself because remember there's that number there. It's a 1x. Or we have something called a constant. And a constant term is a term with no variables. So if I just have like the number 5, that's my constant term. One of my other colleagues that I worked with, she used to say it's constantly alone. There's no variable to change it. So if that helps you remember it, it's a good thing to use. And then a coefficient, that's the number part of the term. So if I have 4y, the variable is y, but 4 is my coefficient. So let's take a look at the chart and see if we can fill it in. For A, we want to look at our variables. So our two variables that we have are x and y. Terms, we have three terms. Terms, again, are held together by the multiplication and separated by addition and subtraction signs. So here's one term, here's the other term, and then there's a constant term. So my terms are 3x. And you do want to look to the sign before it for the sign of the coefficient. So my next term is actually going to be negative 5y and then positive 3. Coefficients, remember they're the number part of the terms. So we have 3 for the 3x. We have negative 5 for the negative 5y. And then 3 is also, it's a coefficient for the constant term. It's just not, we already have 3 listed, so we're not going to write it again. And then on my constants, remember they're constantly alone. So it's the number without a variable. So that's a 3. All right, for our next one. Our variables are still just x and y. Now here we do have x squared, but you don't have to put the squared with it when you're listing the variables. Just x and y is fine. Terms, again, we have 3 terms. Negative 4x squared, 5y, and negative 10. So my terms are negative 4x squared, and we do keep the squared there. 5y, and then negative 10. My coefficients are the number part of the terms, so we have negative 4, 5, and then negative 10 is a coefficient. It's also, though, a constant, so you can list it in both places. And then let's take a look at our last one. We have 7ab minus c. So in this case, we have 3 variables. We have a, we have b, and we have c. Terms, I have 2 terms. I have 7ab and then negative c. Now coefficients, 7 is a coefficient, and because we have that negative c there, again, I want you to get used to if there's a variable by itself, it does have a coefficient, and that coefficient is a 1. And in this case, it would be a negative 1 because it's negative c. And here, because we don't have any coefficients by themselves, we don't have any constant terms, there are no constant terms here. All right, so next we're looking at evaluating expressions. To evaluate an algebraic expression, you substitute known values for variables into an expression and use your order of operations to simplify. So we got to substitute and then use order of operations. So order of operations, just as a review, some people, you may remember PEMDAS. It's PEMDAS. P stands for parentheses or other grouping symbols, like brackets or a large fraction bar. And we'll see that shortly when we do some examples. E stands for exponents. M stands for multiplication. D is for division. A is addition. And S is subtraction. Okay. Now, with order of operations, this is the order that you want to do the problems in. We have created this so that everybody solves problems the same. So sometimes if you look at a problem, if one person uses order of operations and another doesn't, you get different answers. And we kind of needed uniform ways to solve problems so that, we all come up with the same answer. One thing to caution you with is with multiplication and division, even though multiplication comes before division, these two go together. You perform them from left to right when you're doing multiplication and division. So if you have division first, you do that first if it's on the left-hand side of the problem. And same thing with addition and subtraction. Even though they're written this way, you perform them together from left to right. All right, let's evaluate some algebraic expressions. So here, the first one we have is 2a plus 3b, and they want me to evaluate it or solve it when a equals 2 and b equals 7. So what I'm going to do is just plug in or substitute in my values for the variables. So now I'm going to instead of having 2a, I'm going to do 2 times a, which is a 2, plus 3 times b, which is 7. Here we have multiplication and addition. Remember, multiplication comes first, so I'll multiply here. I get 4, keep my plus sign. 3 times 7 is 21. Then I'll add them together, and I get 25. The next one, we have x squared plus y squared minus x times y. So x squared, that is going to be negative 3 squared plus 4 squared minus negative 3 times 4. Now, for the first part, you may notice that I put this in parentheses. If you use your calculator to evaluate it, you need to put it in parentheses because we're squaring x, and x is negative 3. So we're doing negative 3 squared, so it will be negative 3 times negative 3, which gives me a positive 9. If you put it into your calculator and you just do negative 3 squared without the parentheses, your answer will come out a negative 9. So you have to be careful with that and know the difference. Up here, we were squaring the whole number. Down here, because there are no parentheses, I call them glue to hold the negative to the 3. Really what we're doing is we're squaring the 3, which gives us 9, and then taking the opposite. So it is a difference. Try it on your calculator to see the difference. And I'm doing exponents first because we have, even though we have parentheses, they're just around a number. It's not around a problem. So we have 9 plus, and then we get 4 squared is 16 because you do 4 times 4. Minus, and then here, I'll go ahead and do the multiplication because I did the exponents. Negative 3 times 4 will give me a negative 12. Now keep that in parentheses. All right, now all I have is addition and subtraction left. So I'm going to do it from left to right. So 9 plus 16 will give me 25 minus my negative 12. And remember, when you're dealing with integers, you take it and change it to addition of the opposite. So it's really 25 plus a positive 12. So then my answer becomes 37. Okay, here is our next problem and our last one for evaluating expressions. And for this one, we do have parentheses here. We have a couple sets. We have the large fraction bar, which it's parentheses in and of itself. Even though the fraction bar also means division, we can't do the division until the very last step because we need to have a single number on the top and the bottom. So let's focus on filling in our values. So we'll have 3 plus, and then it's 2. And remember, those straight lines mean absolute value. So 9 minus a negative 2. And that's going to be over 9 plus 2 times negative 2. And absolute value is the distance a number is from 0. So if I do over here, if I looked at the absolute value of negative 5, on the number line, how many spaces away is negative 5 from 0? It is 5 spaces away. Now, if I looked at the absolute value of 5, how many spaces away from 0 is it? It is also 5. And because the definition says the distance a number is away from 0, when we talk about distance, we never have negative distances. Like when I get up in the morning, I don't walk negative 2 miles. I either walk somewhere or I don't. So distance, it doesn't matter what direction you go, you're still recording distance. So distance, when you take something out of absolute value bars, it's always going to be that positive value. So let's start, and really we're going to treat this like two different problems. We're going to worry about solving the top first to get it down to a single number, and then do the bottom. So on the top, the absolute value symbols are like parentheses, so we'll do that first. And we'll do our addition of the opposite. So 9 plus 2 will give me 11. So right now I have this. I have 3 plus 2 is the absolute value of 11. And up here, 2, and then because it's right next to the absolute value means we're going to multiply. So we'll end up with 3 plus 2 times 11 will give me 22. I'm just going to keep the bottom. So on the bottom, we'll have 25, or excuse me, on the top we have 25. And then on the bottom, 2 times negative 2 will give me 9 plus negative 4. And if I simplify that, I end up with 5. And now that we've simplified the top and the bottom to a single number, we can do that division. So this is the only time you kind of hold off on that division. And 25 divided by 5 will give me a final answer of 5. All right, so here we're looking at properties of real numbers. And these are properties that we'll see. You've probably seen them before, and you'll see them a lot in all of your algebra classes. And now that we're working with variables, they'll make more sense than if we were just working with numbers. So our first property is our commutative property. And I always think of this like my commute in the morning. So I leave my house and go to school. And then in the afternoon, I leave school and go home. I always travel the same distance, but I'm going in opposite directions. And that's what your commutative property says. Like you can switch around the numbers for an addition or a multiplication problem and still get the same answer. So I could do something like 6 plus 2. And it's the same as 2 plus 6. Okay? So they both give me 8, but I didn't add them in the same order. Multiplication is the same. We could do 5 times 4, and that's the same as 4 times 5. So that's what your commutative property is. It doesn't work for subtraction and division, only addition and multiplication. Next, we have the associative property. And I always say this is like who you associate with. So we can start off with 2 plus 3 in parentheses and then plus 5. But if I change the grouping symbols, which is what happens in the associative property, I could also do 2 plus, and then in parentheses, 3 plus 5. Both problems will give me the same answer, even though following order of operations, I had a different set of parentheses to simplify first. And it is the same with multiplication, so I could do 5 times 4 in parentheses times 6, and it would be the same as 5 times, and then in parentheses, 4 times 6. So the grouping symbols change, not the order of the numbers, but the way they're grouped changes with the associative property. And again, it only works for addition and multiplication. Next, we have our additive identity. So this is how a number keeps its identity. Your additive identity, I always want you to remember, is 0. That was 0. There we go. So if we do like 5 plus 0, it equals 5. Or 0 plus 5 equals 5. So that's our additive identity. The multiplicative identity is going to be 1. Because you have to think, like, what number could you have in a multiplication problem that will help you retain the original number? And so, like, if I did 7 times 1, I still get 7. Or 1 times 7. So the multiplicative identity is 1. The additive identity is 0. Now over here, we have our additive inverse. And the inverse is I want to take a number and go to 0. So I want to go back to 0. So if I have something like 6, if I add the opposite to it, it gives me a 0. Algebraically, they say A plus the opposite of A equals 0. That's how it's written. So any number plus its opposite will give you 0, and that's your additive inverse property. For the multiplicative inverse, it's a little bit different because I can't multiply by a -1 and get back to my original number. But what I can do is take your original number A and then multiply it by the reciprocal. So remember, the reciprocal is like when you have a fraction and you flip it. And if I do any number times its reciprocal, it will always give me 1. For instance, let me go down here and do this number. If I do 6 times 1/6. Remember, 6 as a fraction is 6 over 1. And when we multiply, we go straight across. So 6 times 1 is 6. 1 times 6 is 6. But if I have 6 over 6, it gives me 1. Our last property is the distributive property. So that says if I have A times the quantity of B plus C, it is the same as AB plus AC. So we distribute multiplication over the addition and end up with our expression here. And we do use the distributive property a lot because a lot of times inside our parentheses we don't have like terms and we can't combine them, but we can distribute the number from the outside. Right, so here I'm just going to give you some examples different than the ones we did on the other page. Like my commutative property, I could do if I just did addition, I could say, 1 plus 2 is the same as 2 plus 1. Associative, let's do multiplication here. So let's do 3 times A times B. And then I could do 3 times AB. And I didn't put the multiplication symbol here because I have the parentheses. And remember, when letters are together, it means multiplication. My distributive property, we could do 5 times x plus 2. So when I distribute, I would end up with 5x plus 5 times 2, which I can go ahead and multiply, and is 10. And then I can't do any more because these are not like terms. We can't add them. And if you can't remember what that is, we're going to look at it shortly. My additive identity, we could do, let's do 10 plus 0, because remember that's your identity, equals 10. Multiplicative identity, we'll do 11 times 1, and we still get 11. Additive inverse, so remember this is where you have to go back to 0. You want it to equal 0. So we'll do 7 plus -7 equals 0. And again, you don't have to come up with these examples. You can come up with your own. Multiplicative inverse, any number times its reciprocal will equal 1. So I'm going to do 5/9. So I'll do a fraction here. Times the reciprocal, which is 9 over 5, will give me a 1. All right, so here we're naming the property identified or illustrated. And this is something you may have to do on like your test or your quiz. They'll give you a property and ask you to name it. Here, notice we have a number plus its opposite and it equals 0. So that's going to be not your additive identity, but your additive inverse. So that one's the inverse, because I think of inverse like reverse, it goes back to 0. Okay, for B, we have multiplication here, and we have -4 times 6x, and then here -4 times 6 times x. Notice the order of the the letters and the numbers don't change, but the grouping does. So that's going to be your associative property. Hold on, let me erase that. Associative. we'll say associative property of multiplication. All right, and then down here, we have y plus 3 plus 2, so it's all addition, and then y plus 3 plus 2. Again, the order didn't change, but the grouping did. So that is your associative property of addition. And then our last one, we have 5 times the reciprocal of 5, which is 1/5, equals 1. So that's our multiplicative inverse. All right, so here we're just practicing the distributive property again. So we're going to use the distributive property to rewrite our expression. So we're going to distribute the 3 to the 2x plus 4. So we're going to multiply. So 3 times 2x will give me 6x. 3 times 4 will give me 12. And then, again, they're not like terms, so I can't add them together. Here I'm going to distribute my negative 2. So negative 2 times positive 3x will give me negative 6x. Negative 2 times positive y, and remember there's that 1 there. So negative 2 times positive 1 will give me negative 2y. And then there's another 1 there. Negative 2 times negative 1 gives me 2 negatives, make a positive 2z. And again, I can't do any combining, so that's my final answer. And then here's our last one. We're going to distribute 5 to all 3 terms. So 5 times 2 will give me 10. 5 times 3a will give me 15a. And 5 times negative 4b will be negative 20b. All right, and the last topic that we're going to look at with our notes here is simplifying algebraic expressions. So we can simplify algebraic expressions by combining like terms. So we need to combine like terms. And then the next part is like terms are 2 or more terms that have the exact same variables. So they have to be the exact same variables. And the variables are raised to the same power. Then you add your like terms by adding their coefficients. Oops. So by adding their coefficients. Okay. So, for instance, if I have something like 5x plus 7x, what you're looking at, and I always call it like the last name. So you're looking at the variable. The coefficient doesn't matter. It's the variable part. If the last name is the same, then you can add it. If the last names are different, you can't. They're from different families. But here we have 2 x's, so you add your coefficient and keep the variable the same. So this would equal 12x. Now what if I had something like 4x squared plus 7x? Are these like terms? And if you look here, look at the last names. I have x squared and I have x. Remember, they have to have the exact same variables and coefficients. And in this case, they don't. We have x squared and x. 2 different last names. So really with this, the only thing I can do is leave it as it is. I can't combine it. It is done. So it is all that we can do. And the last one I want to show you, what if I have something like 7xy plus 9yx? Here, are my last names the same, or my variables? And if you look, I have xy here and yx here. Now you're like, they don't look the same, but they are the same variables. And remember, what holds the x and the y together? It's multiplication. Remember our commutative property? It's okay if they're in a different order. They don't have any exponents, so they're the same. They just have x on both and y on both. So here, it's kind of like I say they have the same last name, but they spelled it wrong. So because they are the same, we can add these together and make it 16, and then you can choose your order, xy or yx, but they can be combined. Okay, so here's the last part, and we're just going to simplify some algebraic expressions. So we want to, again, look for those like terms. And the big thing here is when we simplify, you don't have to get to a single number. It's okay to have an expression, so have 2 or 3 terms or more. So for our first one, I have 3y, and then I have 8y. So those are like terms, so I'm going to add them together. And 3 plus 8 will give me 11y. And then I have constant terms. So I have -7 plus 2. And you always look to the sign before your term to see what the sign of the number is. So, it's like the same as -7 or -7. -7 plus 2 will give me a -5. And then 11y minus 5, I can't do anything with. So that's my final answer there. And here, if it helps you to see the like terms better, underline them with a highlighter or highlight them in different colors or use colored pencils to circle them if it helps you identify those like terms and combine them. So for our next one, let's see here. I see an A, so I'm going to underline that, and then I'm going to look for other A's, and I have 12A. So -7A plus 12A will give me 5A. And then let's go to red. Let's see here. I have 3b and -17b. So when I combine those, 3 minus 17 will give me -14b. And then my last part, I think I have some constant terms. I have -6 and -20. When I combine those together, it's going to give me -26. And I can't do any more, so that's it. All right, let's see here. Our next one. For this one, we have to first, we want to distribute. If you have the distributive property in there, before you combine like terms, distribute. So 5 times 3x will give me 15x. Plus 5 times 7 is 35. And then I have my plus 4x and plus 10. So now that I've distributed and I have all terms without any multiplication in there for the distributive property, I can add them. And I have 15x and I have 4x. So that gives me 19x. And then I have constant terms, 35 plus 10. So that'll give me plus 45. Okay, now our last one. We have to distribute twice. For the first one, we have that negative sign on the outside. That means to take the opposite of everything on the inside. And really, if you don't see a number there, remember, it's that invisible 1. So it's -1 times everything on the inside. So -1 times a positive 3a gives me a -3a. And a -1 times a -7 gives me positive 7. So I've taken care of that distribution. Now here, I have a -2 that I have to distribute to everything on the inside. So it's going to give me -2a minus 16. And then I'll combine my like terms. So we have -3a and a -2a will give me a -5a. And then 7 minus 16 will give me a -9. And that's it for combining like terms.